Thank Dave for inviting me and the Apparatus Committee and my institution for supporting me here. I'm going to talk about high-speed video and play around with high-speed cameras and show you some things I've been doing. Really is kind of an overview of what's available. There's some exciting things in the high-speed world that have become affordable very recently. And also I have an infrared camera. If you guys have seen, you know, there's at least one other one floating around here. It's an iPhone attachment. So I'll show you a little bit about what that does. And the slide advances when I do, no. Okay. All right, let's cut up a little bit. So we'll start with just a little bit of overview. We're skipping an entire century here. 1906, was that the...
1900s by cutoff.
Okay. So just a little bit of overview of the CCD technology, and we have another talk coming up that's going to talk about the difference between CCDs and CMOS. So if I say anything incorrect there, you can correct me. Talk about what is high speed and what you can do with some of these consumer things. Talk about the cameras over here, and then just show a whole bunch of video examples, ideas to get you thinking. Infrared down there, this is barely readable. Some recommendations, and if we get time, we'll talk a little bit about analysis. Got to click that one. All right, so CCD sensor, you know, it's this thing in the upper right corner. It's sensitive to light. It's an electronic device, lots of little pixels. Photon comes in, excites a photoelectron, which is stored. Not working. Let's see. It's supposed to just work by clicking. All right. Excites a photoelectron, which is stored in this pixel until the exposure is done, and then they're moved off with a series. Come on. A series of gated electronics to move them. We normally, I'm just going to skip over some of this really quick. Get on the exciting videos. We normally use this rain bucket image to describe how it works. So the photons are collected and they build up electrons here in these buckets. And then the electrical signals on the chip move them off and dump them. The reason I say that, and dump them, they're measured by some charge to digital converter. So you know how much charge was on each pixel by the time it got down here. A lot of stuff going on the chip. And I say that for a couple of reasons, just to give you an idea of what's going on. Let's see what I wanted to say. A little bit about noise. So you can get thermal excitations. The really fine cameras are often cooled to eliminate some of that. Of course, the process of reading it out. If you do that, try to do that really fast. You sometimes get. Am I talking really fast? You're good. You sometimes get a lot of noise. If those buckets get full, if you get more electrons than can actually get in there, you get blooming. And the image is spread out over a number of pixels. Limits on the number of precision you can get. If you're doing this really quickly, you need a lot of photons to get into each of those buckets. If it's really quick, there aren't a lot of photons. Do this right. And you get, so if there were 10 photons in each bucket, you know, that's a stochastic process. You're going to have an error that's on the rate of the square root of 10. So you get between 6 and 14. If your background is that dim, then that's a lot of noise coming out in the photograph. So completely overexposed, here's your review of information theory. All ones, everything is lit up, you know, full things. And 0, completely black. Those contain the same amount of information, basically. The interesting thing is when you have some contrast between the pixels on the screen. The consumer cameras do a lot of optimization. One of the slides I want to talk about what they're doing and how you can get around it. They're optimizing for a signal to noise, assuming a certain good photograph might be of your kid playing soccer. Sometimes in physics, that's not what we're looking for. The signal is not what the camera is expecting. So I have one new recommendation on how to get around that. Let's see, so the readout sequence. In a standard video that you can see on TV that was taken at 30 frames per second, this readout sequence, there's something to clear the CCD, or at least enable the light sensitivity. It collects light for a period of time, and then you read out the data from the CCD. So that all happens on a regular camera 30 times a second. You get up to 1,000 times a second. That's going very fast. That collect light step, as Tom was saying, these hour-long exposures, 30-minute exposures for some of the earliest photographs, all the people blur out of it. If you're looking at very fast-moving objects, even a fraction of 1,000th of a second, something can move. So I'll talk to you a little bit about that down here. Okay, summary, what I wanted to get you out of the CCD. High speed requires a lot of light. It generates a lot of data very quickly, and the camera compromises between resolution, so usually the high-speed modes will reduce the resolution that you're seeing on the camera. The shutter speed, you're exposing for longer time to get enough photons on there. The dynamic range, whether you're digitizing that into 8 bits or 4 bits or something like that, so you lose a lot of things. Jerry was commenting earlier about some of the high-speed cameras looking very dark. They have very little contrast. You get the black, and you get a couple of photons. You can adjust the contrast on that to make it look very bright, but looks a lot like some of the original photographs. So pushing the techniques. The other thing that's done is the images are compressed, and that actually allows the higher data rates to get that data from the chip onto a storage method. Also, they'll limit the amount of time you can take data. So if the storage is all really right on that same chip, if they're doing something clever very near that chip, they might limit you to a few seconds. And that's actually one of the things the Nikon camera does on the high-speed modes. How much speed do you need? So I'll get to the fun stuff. You zoom that up just a little bit. So I put on a range of speeds. Up at the top there it says snail. On the bottom we have escape velocity. I found a couple of different velocities for snails. So apparently let's see, walking speed. So I've got, it's kind of a complicated table. So I've got miles per hour and centimeters per second for these speeds. And then over in these columns I have frame rates. So 30 frames per second is your standard video. 240, 400, 1200, these are now accessible in consumer grade cameras. So let's just look through a couple of these things, how fast something moves if you are doing that. So if you're on a bicycle at 15 miles an hour, now Dave's got a better bike, he rides much faster I think, but this
Actually,
is how
Sam
fast I bike. Oh, Sam's the cyclist, okay. So about 15 miles an hour, so every frame, even at 30 frames per second, you're moving 22 centimeters. That's pretty good. Things like ripples on water at half a mile an hour, a mile per hour. You're moving on the order of a few centimeters, or a centimeter-ish. But at 240 frames per second, you see it's kind of exciting. You're seeing details that happen on the order of a millimeter during each frame. So that's kind of exciting. Water gets really cool at that speed. Projectile launcher we're familiar with in the physics lab. There are a couple models depending on the setting that launches a ball that goes across the room. It flies about 2 meters, has a hang time of about 2 seconds. So 5 to 10 miles per hour kind of thing for that. Standard video, the ball images are going to be separated by a few centimeters, 7 here, 15, depending on the speed and where it is in the arc. So you get a lot of distinction as to where the ball is on the frame. It goes up. About 2 seconds or something to get across the room, second and a half. That'll give you about 60 images of the ball. That's a lot of data. You do that at 400 frames per second for 2 seconds, that gives you 800 images. They move pretty slow. So let's see, at 5 miles an hour, we're around the millimeter range. What you can't do, getting up here, so everybody thinks high-speed video, you want to reproduce, so here's my 20th century reference, Doc Edgerton's work from MIT. And you want to get this apple. And the way he did that, of course, he had a aperture that was open for a long time, and he did it with a very fast strobe that would strobe for a very, very short period of time. And he timed that strobe, so this gunshot through the apple thing, he timed that strobe with a microphone. And knowing the speed of sound and the speed of bullet and accounting for any delay in his electronics, he could time that flash to go off exactly where the bullet he wanted. Single image, very, very fast, exciting. Speed of a bullet, here we're getting down speed of sound, speed of a bullet. At 1200 frames per second, the bullet is going to travel 34 centimeters per frame. So if you happen to catch the bullet in the apple, just before it's going to be over there, just after it's going to be over there, It's going to be moving very fast. If you don't have a very fast shutter, and these consumer cameras won't do it, you won't really see much detail with the bullet. So that's exciting. Kind of limiting, but I do have one example of something nearly the speed of sound. This ping pong ball cannon, the vacuum cannon. And you can see some things there. You can put some limits. I wouldn't say it's terribly precise. You get a lot of blurring. Speeding bullets, speeding sound. Here's another fast thing that actually is kind of